And we have one colleague from Faculty of Technology and Metallurgy, also from University of Belgrade. And we were doing on determining the cause of incorrect work of bumper paint robots reducer. This is practically structural problem. But when you see the heading, you would think that we are doing something connected to the robots. Robots are used for some precise tasks, and they replace human operators in those tasks. When you have some, I don't know, for instance here, we have a painting robot. When you have a painting workshop, it is toxic environment for a human operator, and the tendency is to replace the human operator with the robot. Also, the work would be done better. You will get a lot more precise work, and you will get great savings in time and material needed for the operation. And in this paint shop, a failure occurred on one of the robots, and the cause of that failure was practically the rigidity of this bearing support structure. And the complete research was conducted, and it consisted of numerical and experimental approach. Here you can see our construction. It's a construction made of beams and one plate, and on that plate are positioned the housing of those housings of the robots are positioned, as you can see in this picture. And one of them failed, so we conducted several operations to remove, to practically repair the damage in the end. So, as you can see, the robots are placed in the central part of the structure, while the fenders, automobile fenders that are painted by those robots, are moving on the sides of this platform. So this is the only operation that is done in this workshop. So only robot work could cause some failure. So here are those typical robots, and this is our construction of interest. I have explained it before, and now we firstly performed the static and dynamic analysis. You can see here boundary conditions, and later you will see the loads. This is the structure. This is it is done. Computations are done in a program named COMIPS, which is developed at the Faculty of Mechanical Engineering, and it is based on finite element method. And it is, for me, it is better than other commercial programs, because all the time I can have complete control over the mesh and over the equations. So here you can see a computational model. X is a longitudinal direction, Z is transverse direction, and Y is a vertical direction. It is important for some later discussion, later. So those are positions of the robots, and the static calculations were done firstly. And we assumed that the forces, static forces, that robots cause are around 10 kilonewton. And we applied in the spots of the robots, we applied forces, and we computed displacements. And after that, we computed rigidity in all directions. And the rigidity was satisfactory only in Z direction. So rigidity and stiffness in directions X and Y were not satisfactory. So this is the first step. The second step was dynamic analysis. We induced concentrated masses. I don't think that you can see them here. Concentrated masses in 3 directions. They simulate masses of the robots. And practically, why did we done this dynamic analysis? Because those robots, they move in several directions. They cause inertial forces, and thus they have oscillations at so many frequencies. And the frequencies of those robots would coincide to the natural free frequencies of the structure, and they will cause resonant behavior of the whole structure, and they will cause the failure in the end. So this was the second step. Dynamic calculations were done, and we obtained free frequencies of this structure. And I don't think that I have that analysis in this presentation, but we obtained 20 free frequencies that are lower than 20 Hertz, and only 5 of them was considering some peripheral oscillations of those parts. That means that all low frequencies were in that zone, in the zone of the robots. So a resonant behavior is expected. And now, after this, we conducted another analysis. This is the place of excitation, and we practically calculated dynamic gain factor when we have excitation in X, in Y, and in Z direction. And here you can see the results of that analysis. The first row represents excitation in X direction, and there is a response in X, in Y, and in Z direction. When you have excitation in X direction, you have a frequency on the horizontal axis of diagram, and on the vertical is a dynamic gain factor. And as you can see from this picture, you have a frequency of around 15 Hertz, which is in correspondence with the previous analysis, and you have a dynamic gain factor of around 60. So you have resonant behavior of the construction. In the Z direction, you have 2 times smaller dynamic gain factor, and in X direction it is negligible. It is around 4. And when you have excitation in Y direction, you have a dynamic gain factor in X direction of around 60. Those 2 are negligible, and here you have a dynamic gain factor of around 50. So this was theoretical part of the analysis. Then visual inspection of the structure was done, and unfortunately the condition of the construction, the results that we get using computations were bad enough, but the condition of the construction was even worse. So we expected to get measurements even worse than our computations. So why I'm saying this? Because maintenance and the installation of the construction was poor at the first time, and maintenance, I think that they never did it. Because you have some girders that were plastically deformed, some screws were loosened, some welded joints were not done properly. When you have a plate when you need welded joints all along the girder, but you have welded joints on, I don't know, every 2 or 5 meters even. So we were prepared to have even worse measuring results than our computational results. And they were, so we measured accelerations and we measured displacement on Robot 2 and Robot 3 carrier. And we conducted experiments. I think one was done now, and the other one was done in 2 months. So the first one, on Robot 2 carrier, we get accelerations of around 4 meters per square second. And in the next measurement, we got acceleration of 5 meters per square second. That means that are slightly even worse results in those months. So reparation process was conducted. Reparations were actually small. We modified those carriers of the robots, and small improvements in the global construction were done. And after that, we measured accelerations and displacement, and they were not great, but they were within the limits. And afterwards, one more proof is that this construction and this whole system is working for several years without any failure. So this is circumstantial proof of our solution. Okay. This is resume of everything that I have already said. I don't think that we need to start being there. So thank you for your attention, and if you have any questions, you can contact me. This is my email address. Thank you.
Thank you, Dr. Anna. Any questions to Dr. Thank you. I have one if you do not mind. Thinking about any kind of damping, internal damping of profiles to minimize the vibration of the platforms.
Sorry, I'm not sure that I understand.
I was asking if you use any kind of damping material.
Yes, we tried, but I think that would be too expensive. And this was the simplest. Practically, the original construction was not that bad as it is placed. Because some stiffeners that would improve dynamic behavior were left over. Yes, we know.
Okay, thank you so much.
Thank you.
Okay, I think we ended our session. You want to leave the class?